The morning air hung thick with coastal fog as Soviet ground crews at Centralnaya Uglovaya airfield watched an enormous shape emerge from the clouds. July 29th, 1944. 30 kilometers east of Vladivostok. The aircraft descending toward them was unlike anything in the Soviet inventory. 4 massive radial engines, a wingspan that seemed to stretch forever. A gleaming aluminum fuselage reflecting the pale morning light. The Boeing B-29 Superfortress designated ramp tramp touched down on Soviet soil, and with that landing, Stalin's engineers were about to discover exactly how far behind America the Soviet Union had fallen. Captain Howard Jarrell brought his crippled bomber to a stop, relieved to have reached friendly territory. His crew had been hit by anti-aircraft fire during a raid on the Showa steelworks in Manchuria. 2 engines knocked out, fuel running critically low. No way to make it back to their base in China. Vladivostok was the only option. What Jarrell didn't know was that his B-29 would never leave Soviet territory. What he couldn't imagine was that Soviet leader Joseph Stalin would order the complete disassembly and copying of his aircraft. And what neither American air crews nor Soviet engineers could have predicted was how this single emergency landing would expose the staggering gap between American and Soviet industrial capability. The Superfortress sitting on that fog-shrouded runway represented everything the Soviet Union lacked, not just an aircraft, an entire industrial philosophy, a manufacturing ecosystem that Soviet planners had spent years trying to build but couldn't match. And Soviet engineers were about to spend the next 2 years measuring every rivet, photographing every component, and confronting the uncomfortable truth that copying American technology was far easier than replicating the industrial capacity that produced it. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The B-29 Superfortress was the most technologically advanced aircraft flying in 1944. When Boeing began development in 1942, the goal was to create a strategic bomber capable of attacking targets across the vast Pacific. The result was revolutionary. The aircraft featured pressurized crew compartments, allowing operations at altitudes above 30,000 feet, where Japanese fighters struggled to intercept. 4 Wright R-3000, 350 Cyclone engines, each producing 2,200 horsepower, gave the Superfortress unprecedented range and payload capacity. The bomber could carry 20,000 pounds of ordnance across distances exceeding 3,000 miles. But the B-29's most remarkable feature was its remote-controlled defensive armament. General Electric had designed an analog fire control system that linked 5 gun turrets through electrical servos and mechanical computers. A single gunner could remotely aim and fire multiple weapons simultaneously. The system calculated ballistic corrections for altitude, airspeed, temperature, and target movement. Nothing like it existed anywhere else in the world. The aircraft's construction was equally sophisticated, all aluminum airframe, dual-wheeled tricycle landing gear, flush-riveted skin panels to reduce drag. Every component reflected American mass production techniques refined through years of automotive manufacturing experience. The B-29 wasn't just advanced. It was the physical embodiment of American industrial might. Soviet aviation in 1944 told a different story. The most capable Soviet bomber was the Petlyakov P-8, a design that first flew in 1936. Only 93 were built during the entire war. The P-8 used fabric-covered control surfaces. Its range was barely half the B-29's. Its bomb load was a fraction of what the Superfortress could carry. Soviet aircraft, production focused on quantity over sophistication. The Il-2 Sturmovik ground attack aircraft was produced in enormous numbers, more than 36,000 by war's end. But it was fundamentally simple: steel construction, limited instruments, no pressurization. Soviet fighters like the Yak-3 and La-5 were effective but conventional. There was nothing in the Soviet inventory that approached the B-29's complexity or capability. Stalin recognized this gap. Beginning in 1942, the Soviet leader repeatedly requested that America supply B-29 bombers under the Lend-Lease program. Through that arrangement, The United States had already delivered over $11 billion in war material to the Soviet Union. Thousands of aircraft, including Bell P-39 Airacobras and Douglas A-20 Havoc bombers, over 400,000 trucks and jeeps, tanks, locomotives, food, oil. But strategic bombers were excluded. American military planners had no intention of sharing their most advanced weapons technology with a nation they deeply distrusted. The Soviet Union was an ally only because Germany had invaded in June 1941. Once the war with Germany ended, American strategists understood that Soviet ambitions would threaten Western interests. Providing Stalin with strategic bombers would only strengthen a future adversary. Stalin's second request for 120 B-29 seconds in early 1944 was simply ignored. The United States offered no explanation and made no counter-proposal. The message was clear. If the Soviet Union wanted strategic bombing capability, they would have to develop it themselves. Except they couldn't. Soviet aeronautical engineering had produced capable fighters and ground attack aircraft. But strategic bombers required capabilities the Soviet aviation industry didn't possess. Long-range, high-altitude flight demanded sophisticated engines, pressurization systems, advanced avionics, precision manufacturing at scale. Every attempt to develop indigenous designs had failed to match Western performance. The Tupolev ANT-64, later designated Tu-10, was under development as a potential long-range bomber. But the program was progressing slowly, hampered by engine problems and materials shortages. Soviet engineers knew their design would be inferior to the B-29, even if development succeeded. The technological gap was simply too wide to bridge through conventional means. Then Ramp Tramp landed at Vladivostok, followed 3 weeks later by another damaged Superfortress that crashed near Khabarovsk after its crew bailed out. Then 2 more B-29 seconds in November. General H. Arnold Special on November 11th. Ding Hao on November 21st. Both were damaged during raids on Japanese targets and diverted to Soviet territory when their crews couldn't make it back to base. The circumstances were legally straightforward. The Soviet Union was not at war with Japan in 1944. Stalin feared that any open cooperation with American operations against Japan would provoke Japanese retaliation against vulnerable Soviet positions in the Far East. Under international law, military aircraft from belligerent nations that landed in neutral territory were subject to internment. The crews were taken into custody and eventually allowed to escape into American-occupied Iran in January 1945. Washington quietly accepted the situation. Maintaining cordial relations with Moscow remained a priority despite growing tensions. The War Department even instructed returned airmen to remain silent about their time in Soviet hands. But the aircraft themselves were not returned. Stalin saw an opportunity that would fundamentally alter Soviet air power. Rather than continuing to struggle with indigenous bomber development, he would simply copy the B-29. Every component, every system, every manufacturing technique. The Soviet Union would reverse engineer American technology and produce their own superfortress. On August 20th, 1944, Stalin summoned Andrei Nikolaevich Tupolev to the Kremlin. Tupolev was one of the Soviet Union's most accomplished aircraft designers. He had spent years developing bombers for the Soviet Air Force. The Tu-2, introduced in 1942, was among the war's best tactical bombers. But Tupolev had also spent time in one of Stalin's prison camps, arrested during the Great Purge of 1938. He understood the stakes of disappointing the Soviet leader. Stalin's instructions were direct. Examine the captured B-29 seconds, copy them exactly, produce flyable duplicates within 2 years. No excuses. No explanations about why certain features couldn't be replicated. The Soviet Union would have strategic bombers identical to America's. Tupolev's life depended on success. The order was insane by any rational engineering standard. The B-29 represented at least a decade of American aeronautical advancement. Thousands of specialized components. Manufacturing processes the Soviet Union had never mastered. materials that weren't available in Soviet industry, electronics that Soviet factories couldn't produce. Tupolev knew immediately that perfect replication was impossible, but he also knew that explaining impossibility to Stalin was suicidal. Lavrenti Beria, chief of Stalin's secret police, would be monitoring the project personally. Failure would mean arrest, probably execution, possibly torture first. Tupolev had survived Stalin's prisons once. He had no illusions about surviving a second time, so Tupolev accepted the assignment. He would copy the B-29 as precisely as possible. He would document every deviation from the original. He would substitute Soviet materials where American equivalents were unavailable. He would create the illusion of perfect duplication even while making the compromises necessary for Soviet production, and he would pray that Stalin accepted the result. The 3 intact B-29 seconds sat at Centralnaya Uglovaya through the autumn of 1944, while Soviet authorities debated how to proceed. The crashed bomber near Khabarovsk was stripped for parts. The 3 flyable aircraft received Soviet Red Star markings in place of American insignia. They were assigned new serial numbers based on their original American designations. Ramp Tramp became 256 Black. General H. Arnold Special became 365 Black. Ding Hao became 358 Black. In January 1945, Lieutenant Colonel Semyon Rydel arrived at Vladivostok with orders to ferry Ramp Tramp to Moscow. Rydel was a test pilot and engineer with the Soviet Naval Aviation. He spoke English, a rarity among Soviet military personnel. He had experience with American Lend-Lease aircraft, including the Douglas A-20 and North American B-25, but nothing prepared him for the B-29. Rydel and his team spent weeks studying the Superfortress before attempting to fly it, using English dictionaries and technical manuals found aboard the aircraft. They labeled every switch, every gauge, every control in Russian. The cockpit was incomprehensible without translation. American instruments used scales and units unfamiliar to Soviet pilots. The electrical systems operated on different voltage standards. Even basic procedures were foreign. The B-29's complexity was overwhelming. 4 throttles controlling engines whose power output exceeded anything in the Soviet inventory. A pressurization system that maintained cabin pressure at altitude. Remote gun turrets operated through electrical servos, autopilot systems, radar, radio equipment more sophisticated than anything Soviet industry produced. Every system revealed another layer of American technological advancement. On January 9, 1945, Rydel climbed into Ramp Tramp's pilot seat with A.F. Chernov as co-pilot. The engines started without difficulty, their deep rumble unlike any Soviet power plant. The takeoff was smooth. The Superfortress lifted off Vladivostok's runway and turned toward Moscow. The flight revealed the B-29's extraordinary capabilities. Cruising at altitude, the pressurized cabin was comfortable, while the thin air outside would have required oxygen masks in any Soviet bomber. The engines purred steadily, delivering consistent power hour after hour. The fuel consumption was precisely predictable. Every system worked as designed. Soviet aircraft, by comparison, were temperamental. Engines failed, systems malfunctioned, maintenance was constant. Soviet pilots joked that keeping an aircraft flying required as much skill as flying it. But the B-29 just worked. American reliability was evident in every aspect of the aircraft's performance. Ramp Tramp arrived in Moscow and was delivered to the Central Aerohydrodynamic Institute at Zhukovsky, just outside the city. The other 2 intact B-29 seconds followed soon after. Stalin's engineers could finally begin the detailed examination that would expose exactly how far Soviet aviation had fallen behind American capabilities. The initial inspection teams walked around the Superfortresses in something approaching disbelief. The size was staggering. Wingspan of 141 feet, fuselage length of 99 feet, empty weight of approximately 74,000 pounds. The scale alone exceeded anything Soviet factories produced. But size was the least remarkable aspect. Engineers examining the external surfaces noted the flush riveting that created smooth aerodynamic contours. Soviet aircraft used raised rivet heads that increased drag but were faster to install. The B-29's skin panels fit together with tolerances Soviet manufacturing couldn't match. Gaps between panels were minimal. Surface finish was remarkably smooth. The landing gear was a revelation. Dual wheels on each main gear leg, tricycle configuration with nose wheel steering. Soviet bombers used tail wheel configurations that made ground handling difficult and limited forward visibility during taxiing. The B-29's tricycle gear was heavier, but provided far better ground control and reduced takeoff and landing distances. The engines dominated initial examinations. The Wright R-3350 Cyclone was an 18-cylinder twin-row radial producing 2,200 horsepower. For comparison, the most powerful Soviet radial engine, the Shvetsov A-82, produced only 1,700 horsepower from 14 cylinders. The American engine extracted 30% more power while weighing only slightly more. Engineers measuring the R-3350's components discovered precision manufacturing that Soviet facilities couldn't replicate. Crankshaft machining tolerances were measured in thousandths of an inch. Cylinder head castings showed no porosity. Piston rings seated perfectly. Every internal component reflected quality control standards Soviet industry had never achieved. The supercharger system particularly impressed Soviet engineers. Twin-speed, twin-stage. Supercharging maintained manifold pressure across a wide altitude range. Soviet engines typically used single-stage superchargers with limited altitude performance. The American system was mechanically complex, requiring precision gearing and intercooling that Soviet manufacturers struggled to produce. More concerning was the engine's reliability. American crews reported the R-3350 could operate for hundreds of hours between overhauls. Soviet radial engines required overhaul after 50 to 70 hours. The difference reflected fundamental approaches to design. American engines were built with generous tolerances and robust components. Soviet engines prioritized weight savings and simplicity over durability. Inside the Superfortress, Soviet engineers encountered systems that simply didn't exist in Soviet aviation. The pressurization maintained cabin altitude of 8,000 feet, while the aircraft flew at 30,000 feet. Soviet engineers understood the principles, but lacked experience implementing them. Pressure bulkheads, sealed doors, automatic pressure controllers. Every component was sophisticated and precisely manufactured. The environmental control system maintained comfortable temperatures throughout the pressurized sections. Heated air from engine exhaust passed through heat exchangers. Distribution ducts carried warm air to crew stations. Soviet bombers had minimal heating. Crews wore heavy flight suits and endured freezing temperatures at altitude. American crews operated in shirt-sleeve comfort, but the central fire control system represented the most profound technological gap. General Electric's system linked remote gun turrets through a maze of electrical servos, mechanical computers, and optical sights. A single gunner, in the upper forward position, could aim and fire guns in multiple turrets simultaneously. The system compensated for aircraft speed, target movement, gravity, temperature, and humidity. Soviet engineers disassembled the fire control equipment with something approaching reverence. The analog computers were mechanical marvels, differential gears, cams, precision bearings. The electrical servos responded instantly to control inputs. The optical sights used high-quality lenses Soviet optics manufacturers couldn't produce. Every component revealed American engineering at its finest. Attempting to copy this system would require developing capabilities Soviet industry didn't possess. Precision gearing, reliable electrical motors, high-quality resistors and capacitors, sophisticated relays. Soviet electronics were crude by comparison. Vacuum tubes were unreliable. Components varied in specifications. Quality control was inconsistent. The examination teams compiled reports that painted a devastating picture. The B-29 wasn't just an advanced aircraft. It represented an industrial ecosystem the Soviet Union lacked: specialized alloys, precision manufacturing equipment, skilled workers, quality control systems. supply chains delivering consistent components. None of it could be quickly replicated. Tupolev understood the implications immediately. Stalin had ordered perfect copies. But perfect copies required perfect manufacturing, and Soviet industry was nowhere close to perfect. Every system in the B-29 would need to be re-engineered to accommodate Soviet materials and manufacturing limitations. The result would look like a superfortress, but perform quite differently. The decision was made to completely disassemble General H. Arnold's Special. Every component would be measured, photographed, weighed, and documented. Ding Hao would remain assembled as a reference. Ramp Tramp would continue flying to gather performance data and train Soviet pilots. The crashed bomber's components would provide spare parts. Over 900 Soviet factories and research institutes were mobilized for the project. Tupolev designated it Aircraft Number 64, though everyone involved knew it as the 2-4. Stalin's deadline remained fixed. 2 years from project start to first production aircraft. It was an impossible timeline, but no one dared suggest extending it. The dismantling of General H. Arnold's Special began in spring 1945. Engineering teams worked methodically, removing components in sequence and documenting everything. Each part received detailed drawings showing dimensions, materials, and manufacturing techniques. Photographs captured assembly relationships. Written descriptions noted every detail. Approximately 105,000 individual components were catalogued. Structural members, skin panels, brackets, fasteners, wiring harnesses, plumbing, instruments, controls. The scope was staggering. Every piece had to be replicated, and every replication had to fit together precisely, or the aircraft wouldn't fly. The aluminum specifications presented immediate problems. American alloys used inch-based thicknesses. Soviet aluminum came in metric dimensions. There was no direct equivalence. Converting measurements introduced errors. Structural calculations had to be redone to ensure Soviet materials provided adequate strength. Weight increased slightly with every substitution. Fasteners proved surprisingly difficult. American aircraft used thousands of specialized screws, rivets, and bolts, and standard hardware, NAS specifications. Each type had specific strength and corrosion resistance properties. Soviet factories produced fewer varieties with looser tolerances. Substitutions were necessary, but engineering teams worried about structural integrity. The hydraulic systems used fluids unavailable in the Soviet Union. American specifications for viscosity, temperature range, and corrosion resistance exceeded Soviet capabilities. Soviet substitutes would work, but with reduced performance and reliability. Seals and gaskets faced similar problems. American rubber compounds were superior to Soviet equivalents. The electrical wiring presented a nightmare of compatibility issues. American wire used insulation materials. Soviet industry didn't produce. Color coding standards were different. Connector types were unfamiliar. Soviet electricians had to create entirely new wiring diagrams that maintained functionality while using available components. Every circuit had to be tested and retested to ensure reliability, but nothing compared to the challenges of replicating the engines. The Wright R-3350 Cyclone represented decades of American engine development, metallurgy that Soviet foundries couldn't match, precision machining requiring equipment Soviet factories didn't own, quality control standards Soviet manufacturers had never achieved. The Shvetsov Design Bureau received responsibility for copying the R-3350. Engineers designated their version the AS-73. They began with detailed measurements of every component in the American engine, crankshaft dimensions, cylinder head contours, piston specifications, valve train geometry. Every measurement was converted from inches to millimeters, introducing small errors that would accumulate throughout the design. Soviet metallurgy immediately fell short. The American crankshaft used alloy steel with specific hardness and toughness properties. Soviet steel plants could approximate the composition but not the consistency. Batch-to-batch variations meant some crankshafts would be stronger than others. Quality control testing could identify problems but couldn't prevent them. Cylinder head castings revealed similar issues. American castings were nearly porosity-free, achieving this through controlled cooling and quality inspection. Soviet foundries produced castings with microscopic voids that would expand under thermal stress. Failure rates during testing were significantly higher than American engines experienced. The supercharger proved particularly troublesome. The gearing required precision that Soviet machine tools struggled to achieve. Gear teeth had to mesh with minimal backlash while withstanding enormous loads. American gears were carburized and ground to specifications measured in 10,000ths of an inch. Soviet gears were cut and heat-treated with tolerances 3 times larger. The result was noisier operation and shorter service life. Engine testing began in late 1945. The first AS-73 engines ran but showed problems immediately: overheating, oil pressure fluctuations, vibration. Power output fell short of the R-3000-350's specifications. Soviet engineers made adjustments, revised cooling passages, modified oil galleries, strengthened components that failed during testing. Each change improved performance, but moved the design further from the original. By mid-1946, the AS-73 was producing adequate power, but required more frequent maintenance than American engines. Time between overhauls was approximately 100 hours compared to 300 for the R-3000-350. Soviet pilots would fly with engines that needed constant monitoring and frequent replacement. But they would fly. That was what mattered. The central fire control system required complete redesign. Soviet electronics simply couldn't replicate General Electric's analog computers. The precision mechanical components were beyond Soviet manufacturing capabilities. The electrical servos needed reliability Soviet motors couldn't provide. Tupolev's team made a decision that would have horrified American engineers. They would simplify the system dramatically. The Soviet version retained remote gun turrets, but eliminated most of the automatic computing. Gunners would aim manually with less sophisticated optical sights. Ballistic corrections would be approximate rather than calculated precisely. The system would work, but with far lower accuracy than the American original. Soviet bombers would need more ammunition to achieve the same number of hits. Soviet engineers also substituted 23mm cannons for the American 50 caliber machine guns. This wasn't an improvement, it was necessity. The Soviet Union didn't produce 50 caliber weapons compatible with the American ammunition system. Rather than developing new guns, it was simpler to install weapons Soviet industry already manufactured. The cannons were heavier and had lower rates of fire, but used ammunition Soviet supply chains could deliver. The pressurization system required extensive modifications. Soviet rubber and sealing materials couldn't maintain pressure as effectively as American equivalents. Leakage rates were higher. Cabin altitude at maximum operating height would be 10,000 feet instead of 8,000. Crews would need supplemental oxygen at high altitude, despite being in a pressurized aircraft, another compromise forced by industrial limitations. Throughout 1946, the modifications and substitutions accumulated. Every change moved the Soviet bomber further from the B-29 original. Weight increased. Performance decreased, reliability suffered. But Tupolev and his team had no choice. They were building an aircraft with Soviet materials, Soviet manufacturing equipment, and Soviet industrial capabilities. The result would inevitably be inferior to the American original. Stalin visited the project in summer 1946. He walked around the full-scale mock-up of the Tu-4 that had been constructed for tooling verification. He examined drawings. He questioned engineers about specifications and performance, and he made clear that any deviation from the B-29 design had better have excellent justification. Tupolev explained the substitutions carefully. American aluminum alloys weren't available. Soviet electronics couldn't match American sophistication. Manufacturing equipment limited precision. Every explanation emphasized that these changes were necessary to achieve production within the 2-year deadline. The alternative was continued development, that might take 5 years, or more. Stalin accepted the explanations grudgingly. The Tu-4 would be good enough, not perfect, not equal to the American original, but good enough to give the Soviet Union strategic bombing capability. And perhaps more importantly, the project was forcing Soviet industry to upgrade manufacturing capabilities across hundreds of factories. The long-term benefits would extend far beyond the bomber itself. By late 1946, production tooling was being installed at factory number 22 inches Kazan. This facility would become the primary Tu-4 assembly plant. Templates, jigs, and fixtures were constructed based on the detailed drawings created from General H. Arnold Special's disassembly. Workers who had never seen a B-29 would use these tools to build Soviet copies. The first Tu-4 prototype was assembled in early 1947. It looked virtually identical to the B-29. Same wingspan, same fuselage length, same basic shape. Close examination revealed the differences. Soviet instruments in the cockpit, 23mm cannons instead of 50 caliber guns, slightly different panel lines where Soviet manufacturing processes differed. On May 19, 1947, test pilot Nikolai Rybko lifted the first Tu-4 off the runway at Zhukovsky. The flight lasted 30 minutes. All systems functioned. The engines performed adequately. The aircraft handled similarly to the original B-29. When Rybko landed and climbed out of the cockpit, he reported that Soviet aviation now possessed a strategic bomber. The production aircraft that followed revealed the costs of Soviet manufacturing limitations. Each Tu-4 required approximately twice as many man-hours to build as a B-29. American mass production techniques allowed Boeing to construct superfortresses rapidly with semi-skilled workers. Soviet production relied more heavily on skilled craftsmen who hand-fitted components that didn't meet specifications. Quality control became a constant struggle. Engines failed more frequently than planned. Electrical systems malfunctioned. Pressurization leaked. Hydraulic fluid contamination caused failures. Every problem required investigation and corrective action. Soviet factories weren't accustomed to the tolerances and quality standards needed for such complex aircraft. Despite these difficulties, Tu-4 production ramped up through 1947 and 48. Stalin wanted hundreds of bombers, not dozens. Factory number 22 inches. Kazan was joined by facilities in Kuibyshev and Moscow. By 1949, over 300 Tu-4 seconds had entered service with Soviet long-range aviation. By production's end in 1952, approximately 850 had been built. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The bombers gave Stalin the strategic capability he had demanded. Soviet air power could now threaten targets throughout Europe and potentially reach North America via Arctic routes. NATO gave the Tu-4 the reporting name Bull, acknowledging its threat to Western security. The aircraft that began as American technology had been transformed into a Soviet strategic weapon. But the Tu-4 never saw combat. By the time production peaked, jet bombers were already under development. The British Canberra, first flown in 1949, could fly higher and faster than any piston-engined bomber. American B-29 Stratojet development promised even greater performance. The Tu-4's moment of relevance was brief. Soviet engineers understood this even during development. The Tu-4 was obsolete before production ended, but it served a purpose beyond its combat capability. The project forced Soviet aviation industry to upgrade manufacturing standards dramatically. Precision machining, quality control, materials science, every capability developed for the Tu-4 would benefit subsequent aircraft designs. The knowledge transfer was even more valuable than the aircraft itself. Soviet engineers had studied American design methodology, manufacturing techniques, systems integration, testing procedures. Everything learned from the B-29 informed future Soviet aviation development. The Tupolev Tu-16 jet bomber that followed, drew heavily on lessons from the 2-4 project. Perhaps most significantly, the 2-4 demonstrated to Soviet leadership exactly how far behind American industrial capability they had fallen. Every substitution, every compromise, every quality problem highlighted the gap between Soviet and American manufacturing. Stalin's engineers had been forced to confront uncomfortable truths about their nation's technological limitations. The final accounting was sobering. Soviet factories had employed over 100,000 workers on 2-4 production and related manufacturing. They had created 105,000 drawings to document every component. They had mobilized 900 factories and research institutes, and after all that effort, the result was a bomber inferior to the American original in almost every measurable way. The 2-4 weighed approximately 340 kilograms more than the B-29 despite using the same basic design. Soviet materials and manufacturing variations added weight that couldn't be eliminated. Top speed was approximately 20 kilometers per hour slower, service ceiling was slightly lower, range was reduced. Every performance metric showed the Soviet copy falling short. Maintenance requirements were far more demanding. American B-29 seconds could operate for hundreds of hours between major inspections. 2-4 seconds required attention after every few flights. Engine reliability was particularly problematic. The AS-73 power plants needed frequent monitoring and regular replacement. Soviet bomber crews spent as much time maintaining their aircraft as flying them. The central fire control system never matched American accuracy. Soviet gunners firing manually couldn't achieve the hit rates that American gunners obtained with computer-assisted aiming. In combat, 2-4 seconds would have been more vulnerable to fighter attack than B-29 seconds despite carrying heavier cannon armament. Quantity of fire couldn't compensate for reduced accuracy. Soviet test pilots who flew both the original B-29 seconds and production 2-4 seconds reported the differences directly. One pilot noted that he bumped his head on a cooling duct in exactly the same location in both aircraft, showing how precisely external dimensions had been copied. But the flight characteristics differed noticeably. The 2-4 felt heavier. Controls required more force. Engine response was less crisp. The Soviet copy looked like a superfortress, but didn't fly quite like one. The 3 original B-29 seconds that had made all this possible met different fates. Ramp Tramp continued flying until 1953, serving as a test aircraft, pilot trainer for almost a decade. Soviet engineers respected the American bomber's reliability. Even after thousands of hours of operation, it performed better than newly built 2-4 seconds. Ding Hao was eventually scrapped after being cannibalized for parts. General H. Arnold Special, the aircraft that had been completely disassembled for measurements, was never reassembled. Its components sat in storage, occasionally examined when questions arose about original specifications. The memorial plate honoring General Arnold that had been mounted in the cockpit was removed and kept as a souvenir by Leonid Kerber, one of the engineers who worked on the 2-4 project. The crews of those 3 bombers eventually returned to the United States after their internment. Captain Howard Jarrell and the men who flew Ramp Tramp learned years later that their aircraft had been copied by Soviet industry. They found the revelation simultaneously flattering and disturbing. Flattering that their bomber had been considered worthy of such effort. Disturbing that American technology had been stolen and used to build weapons that might someday threaten American targets. The strategic implications of Soviet atomic weapons development made the 2-4's existence particularly ominous. On August 29, 1949, the Soviet Union successfully tested its first atomic bomb. The device, codenamed First Lightning, was based heavily on American designs obtained through espionage. Combined with the 2-4 bomber fleet, the Soviet Union suddenly possessed credible nuclear strike capability. American defense planners recognized the threat immediately. Soviet 2-4 seconds, based in the Far East, could potentially reach targets in Alaska and northern Canada. Bombers operating from Arctic bases might threaten the northern United States. The entire North American air defense system had to be redesigned to counter bombers that existed only because 3 American B-29 seconds had made emergency landings in Vladivostok 5 years earlier. The Cold War arms race accelerated directly from this technology transfer. American strategists understood that Soviet capabilities now included long-range bombing with potential nuclear weapons. This realization drove development of jet interceptors, early warning radar networks, and surface-to-air missile systems. Billions of dollars flowed into air defense programs specifically designed to counter the 2-4 threat, yet the 2-4 itself was already becoming obsolete. Jet bombers offered performance advantages that piston-engined aircraft couldn't match. The Soviet Union began developing the Tupolev Tu-16 Badger jet bomber in 1950. The United States fielded the B-47 Stratojet in even larger numbers. By the mid-1950s, the 2-4 had been relegated to training and transport roles. Some were converted to aerial refueling tankers. Others served as test beds for new avionics systems. China received a small number of Tu-4 seconds in the 1950s. These aircraft remained in Chinese service longer than in Soviet use, with some reports suggesting they were still flying in the late 1960s. But by then, they were completely obsolete, museum pieces that happened to still be airworthy. The era of piston-engined strategic bombers had ended. The legacy of the 2-4 project extended far beyond the aircraft itself. Soviet aviation industry had been forced to upgrade dramatically to produce even an inferior copy of the B-29. Machine tools were improved. Quality control systems were implemented. Training programs were expanded. Materials science advanced. Every capability developed for the 2-4 benefited subsequent Soviet aircraft designs. The Tupolev Design Bureau learned lessons about systems integration and manufacturing that informed all future projects. The Tu-16 jet bomber incorporated design philosophy absorbed from studying the B-29. The Tu-95 Bear turboprop bomber, which first flew in 1952, used wings and fuselage concepts derived from Tu-4 development. Even the Tupolev Tu-114 airliner shared design DNA with the copied American bomber. More broadly, the 2-4 project taught Soviet leadership about the importance of manufacturing capability in modern warfare. Technology alone wasn't sufficient. Industrial infrastructure mattered. Quality control determined reliability. Supply chain management affected operational readiness. Every lesson learned from copying the B-29 influenced Soviet military-industrial policy for decades. The story also revealed the limits of technology transfer through copying. Soviet engineers had measured every component of the B-29. They had documented every manufacturing technique they could observe. They had replicated the design with remarkable fidelity, but they couldn't replicate the industrial ecosystem that produced American manufacturing excellence. That required decades of development that couldn't be short-circuited through copying. American manufacturing in 1944 reflected years of investment in machine tools, worker training, quality control systems, and supply chain development. Soviet industry lacked all of these advantages. Copying the B-29 design couldn't overcome those fundamental gaps. The result was an aircraft that looked like a superfortress but performed notably worse. This pattern would repeat throughout the Cold War. Soviet designers would study Western technology, copy successful designs, and produce weapons that looked similar but performed differently. The gap wasn't in Soviet engineering talent, which was considerable. The gap was in industrial capability, in manufacturing infrastructure, in the accumulated experience that produced reliable, high-performance systems. The B-29 that landed at Vladivostok in July 1944 represented more than one aircraft. It was a window into American industrial philosophy. Everything about the Superfortress spoke to design priorities. The Soviet Union struggled to match: reliability over weight savings, quality over production speed, pilot survivability over maximum performance. Every choice reflected industrial confidence that components would be manufactured correctly and would function as designed. Soviet aviation had developed under different constraints. Scarce resources demanded weight savings. Limited manufacturing capability required simplicity. Combat doctrine emphasized numbers over sophistication. The result was effective aircraft that achieved their goals through different means, but none approached the B-29's combination of performance, reliability, and crew protection. Soviet engineers examining the captured superfortresses understood this immediately. They weren't just looking at an advanced bomber. They were confronting evidence of industrial superiority they couldn't quickly match. Every system revealed American manufacturing advantages. Every component showed quality control Soviet factories couldn't achieve. The psychological impact was profound. Tupolev and his team had been ordered to copy the B-29 exactly. But exact copying required capabilities they didn't possess. Every substitution, every modification, every compromise was an admission of industrial inadequacy. Soviet engineers could match American designs on paper, but translating those designs into reliable hardware exposed gaps that would take decades to close. The 2-4 project succeeded in its immediate goal. Soviet long-range aviation received strategic bombers. Stalin got his replica superfortresses. The aircraft looked like B-29 seconds and performed adequately, but everyone involved understood that adequate wasn't equal. The Soviet copy fell short of the American original in ways both measurable and intangible. Perhaps the most revealing detail of the entire project was how carefully Soviet engineers copied even minor features of the B-29. Tupolev reportedly insisted on replicating details down to the rivet patterns, terrified that any deviation might be interpreted as deliberate sabotage. In Stalin's Soviet Union, showing initiative could be fatal. Following instructions exactly was survival. This caution produced an aircraft that included features the Soviets didn't need and couldn't properly maintain. American-style tool storage. Placards in translated English. Fastener patterns optimized for American manufacturing equipment. Every unnecessary detail added complexity without improving performance, but no one dared question whether such features should be eliminated. Stalin had ordered exact copies they would deliver. The final irony was that by the time 2-4 production peaked, both superpowers were moving beyond piston-engined bombers entirely. The B-29's moment of supremacy had been brief. Jet aircraft offered such overwhelming advantages that piston bombers became obsolete almost overnight. The technology that Soviet engineers had worked so hard to copy was already being replaced by designs they hadn't yet seen. American B-29 seconds would fly combat missions during the Korean War, suffering heavy losses to Soviet-built MiG-15 jet fighters. The era when propeller-driven bombers could operate in defended airspace was ending. Jets were faster, more maneuverable, and could reach altitudes where piston engines couldn't maintain power. The future belonged to turbojet and turboprop designs, not radial piston engines however powerful. Soviet aviation would make this transition successfully. The Tu-16 Badger jet bomber entered service in 1954, providing performance that made the Tu-4 obsolete. The Tu-95 Bear turboprop bomber, introduced in 1956, could carry nuclear weapons intercontinental distances. Both designs benefited from lessons learned during the Tu-4 project, but both represented Soviet engineering rather than American copying. The story of the captured B-29 seconds and their Soviet copies illustrates fundamental truths about technology transfer and industrial capability. Advanced designs can be copied. Manufacturing techniques can be observed and documented. But the industrial ecosystem that enables reliable production of sophisticated equipment takes decades to develop and cannot be quickly replicated. Soviet engineers in 1944 lacked the machine tools, the materials, the quality control systems, and the manufacturing experience that American industry had accumulated over decades. Copying the B-29 design couldn't overcome those gaps. The Tu-4 performed adequately because Soviet engineers were talented and resourceful. But it never equaled the American original because Soviet industry wasn't equivalent to American industry. This lesson remained relevant throughout the Cold War and beyond. Military technology is inseparable from the industrial base that produces it. Stealing designs provides understanding, but not capability. True technological parity requires developing not just individual weapons, but entire industrial ecosystems capable of producing those weapons reliably and in quantity. The B-29 Superfortress that Captain Howard Jarrell landed at Vladivostok in July 1944 represented American industrial might at its peak. Everything about the aircraft, from its sophisticated systems to its robust construction, reflected manufacturing capabilities the rest of the world struggled to match. Soviet engineers who studied it understood they were examining not just an airplane, but an entire industrial philosophy. Stalin's order to copy the B-29 exactly revealed his fundamental misunderstanding of what made American weapons effective. He believed that replicating designs would produce equivalent weapons. But designs are only part of the equation. Manufacturing capability, quality control, materials science, supply chain management, all these factors determine whether sophisticated designs become reliable hardware. Soviet engineers knew this. They understood that their 2-4 would inevitably fall short of the B-29 regardless of how carefully they copied the design. But they also understood that explaining such limitations to Stalin was extremely dangerous, so they copied what they could, substituted where necessary, and delivered bombers that looked like superfortresses even though they didn't quite fly like them. The result was good enough for Stalin's purposes. The 2-4 gave the Soviet Union strategic bombing capability and demonstrated that Soviet aviation could produce complex modern aircraft. The psychological impact on Western military planners was significant. American defense officials had to assume that Soviet bombers might be as capable as American originals. Better to overestimate the threat than be surprised. But the engineers who built the 2-4 never suffered such illusions. They knew exactly how their aircraft compared to the American original. They had measured the differences. They had documented every compromise. They understood that Soviet industrial capability in 1947 wasn't equivalent to American industrial capability in 1944. The gap was real, measurable, and significant. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.